Okay, welcome back to probability class. But we are done with probability. We are talking about the stochastic processes now. Scary. And yes, today is Wednesday. Okay. And let's see what we talked last class. We actually started stochastic processes or random processes with Poisson random process or Poisson process. And what we said about Poisson was kind of a stepping stone because it's so simple. It's based on actually binomial. When delta t gets smaller, we get Poisson distribution. We also talk about central limit theorem. That was also good to know. What else we covered last class? Yeah, also we talk about another family of distributions, exponential family distributions for finding the interval, the time of actually event. That was actually very good. But what we want to talk today, we want to go more general for all stochastic processes or random processes, and see what is the characteristic of random processes and what is random process in general, definition of that. And it's actually good that random process is something that in nature we see that a lot. We see that a lot. Why? Because in random variable, we just had one variable and distribution, like mean and covariance or variance. And then we said, okay, if we make it a vector, instead of variance, we have covariance. And now we are moving from vector, adding another dimension of time. So instead of having just x and y and x dot and y dot, you have also time here. So it means these points that are, for example, position of robot can make a function of time. Like the time changing, and you can get different vectors. However, this function, I make that discrete in these vectors. That's called vector value function. These vectors are summarizing this function. This function is a function of t, function of time. And we want to talk about this, and that's amazing. So many applications. So many applications of that, especially in robotics, in signal processing, in anything related to signal. We can talk about these things a lot. But today we're going to talk about the characteristic of random processes or stochastic processes. Random processes is stochastic process. And we're going to talk about some characteristic like a stationary. Say, okay, if the characteristic of random process changing in time or not, if it stays stationary in time, we call that random process, a stationary random process. We also have ergodicity or ergodic random process. Ergodic is a little more constrained. we put more constraint in that. So we're going to talk about that. And finally, we talk about white process when there is no correlation between 2 points of the process. That's a simplest version of process. When there is no correlation, we call that white process. Like, for example, we can have white Gaussian process. We can have, for example, a white any other process. White is like a characteristic of random process. When we say is white, it means it's like white light. It gives similar or equal weight to spectrums of light, for example. A spectrum. However, we're going to see how we can connect this to frequency domain. If it a spectral or power spectral density, not now, but next, we're just going to talk about that today, but next class, we're going to see how spectral or power spectral density coming in these topics coming up in these topics, and that's amazing to summarize. Imagine you are summarizing a signal with just some numbers, like a frequency numbers, and that's something that happening with a stationary random process. Stationary random processes can be summarized with frequencies or actually power of those frequencies. We're going to talk about that today, and it's still a start. We need to talk a lot more about random processes in this class. So many things we can talk, especially Gaussian random processes, that they are amazing. It's not just in probability, in AI, in machine learning, you can see Gaussian process. We call that Gaussian process. When relationship between 2 points in that process follow Gaussian rules. That's it. It's called Gaussian process. We're going to see that later. Okay, let's get started. Random process. We already defined that last class, but we can do again. Random process or a stochastic process is actually a family of random variables indexed by time. Okay, I gave example of that robot that moving. Imagine that robot moving in a function, in a continuous function like this. But this is one of the actually like one of the outcomes. Like, for example, this is for omega 1, but this can be different. Like, it can be this, it can be, I'm going to choose different colors. It can be this, and if you, so all family of random variables in time. Each of these is one outcome, so you can have hundreds of them. So this is all together called random process. So the random process is actually two things. You have two things. First, time, and then the outcome, sorry. So we have outcome omega that produce a sample function, and you have this that is time. However, for some kind of random processes, you don't need all of outcomes. One of them is enough because can summarize all the characteristics of that random process. We're going to see that as well. So that's the definition of, let me clean this up. That's the definition of random process. So the random process is a family ensemble. It's called ensemble. All of them called ensemble. That's why we also have ensemble mean. If you have all of these, when I write them, when I draw them as smooth, this means Gaussian, but they are not smooth most of the time. But if it's smooth, this is Gaussian because it's Gaussian smooth. And the mean is this. The mean of all of those together in time gonna make, it's called ensemble mean. Imagine this is time. This red one is the mean. Okay, so we're going to talk about that as well, what is mean. So this is random process. So random process, for each omega, make a function. Make a function. As you can see, each of those is a function. And for each t, make a random variable or random vector. If it's one, is variable. If it's, like for example, in t, for example, equal to ti, here is a random variable. So for each omega, make a function, sample function, or realization. It's also called realization. And for each time, make a random variable. Okay, so this is random process. In other words, you are adding one dimension to random variable, and that is time. So for example, if the random variable is Gaussian, this is like that. But if it's this is random variable, when you go to random process, shouldn't remove it. This is for random variable. It has a mean and variance. For random process, it becomes like this. So this is the mean, and this is showing a covariance or auto covariance. Auto covariance. Because it's by itself. Auto covariance, like saying how this is changing. How this is changing. So it can change all of these areas. They can be full. I didn't put like this is all, can be lots of them. But not go more. They are all in this range. You get the point. What is the difference between, and this is the time side. So you have also time here. That changing. Okay, so we want to study this and lots of applications in signals, in signal systems, signal processing, robotics, networking, and other things. But it's a little kind of get complex. I try to bring this complexity level down with examples and samples, and I explain that with very lower conversational language to understand that better. Okay. Any question? That was just definition. Definition of random process. We had that last class as well a little bit. So interpretation is a random process, is a time-varying random signal where randomness evolve with time. Example, sensor noise is one of them. So noise is always a process. In communication signals, robot motion, uncertainty, that is all random processes examples. This is one example of that. This is, I don't know which process is that, but it's something in top of like a cosine or sine with some, I think is adding cosine with some white noise makes that. This is the example. Another example, this is Gaussian. But I just draw a couple of three realization of that. This is, each of them is for 1 omega. That is also 3, for 3 realization. You can make it a lot, but it's going to be so dense that you can't recognize them. I just made it for 3. Here also for 3. This is Gaussian. As you can see, it's smoother. Here is not smooth, going up and down a lot. So when I'm talking this is smooth, it means if we choose 2 points in one of the realization, they follow Gaussian rule. They follow Gaussian rule. It means the correlation between those 2 points increase when they get close together. It's obvious, because when you are closing to yourself, the correlation become higher and higher. You are depend on these 2 points correlated more. You know, that's why. Okay, so this is Gaussian, but in this probably there is no. That's why I said it look like white noise, because there is no correlation here. So these 2 points, even though they get close, they don't have correlation. Okay, anyway, that's the definition. Key message: a random process models uncertainty evolving over time and breach probability and signals. Okay, thank you for mentioning that. Bridging probability and signals or functions. So yes, we can use that in function optimization. I use that for function optimization. That's one of the things that I use in my papers, function optimization, because you can optimize your function. This is a function, isn't it? That's a function. You can optimize it. How optimize it? With all probability ideas, all probabilistic. You can make, I'm not going to go deeper. Maybe later on we talk about that. But you can optimize because you have a band of those, all of those realization. You choose the best realization that optimize the cost, minimize the cost, or maximize the utility. So that's how you choose the best one. Choosing that is all based off conditional probability and inference to find the best one. We can see that later in this class, I hope. Okay, that's definition of a stochastic process. But basic characteristic. The basic characteristic of random processes means how we can describe a random process with some numbers. Can we say, okay, this random instead of talking about one random process, we just talk about the mean and covariance and correlation? Yes. That's something that is possible in random process. So the first one is the mean. So the mean is average trend over time. If you have many outcomes, you just need to average them over time and get one mean. That's the mean. For example, in that example, the black one is just mean of those. This mean also called ensembled mean. Means it's coming from all of outcomes. All of omegas. Okay, so that's why ensembled mean is called ensembled means. So we need to see this because we have other means too. The mean that coming from one of them, for example, is what we call that one. We're gonna see that. And if these two be equal, if the mean of one of them be equal to mean of all of them, or ensemble mean, that is a good characteristic of that actually random process that later on we're going to see that in ergodicity. Okay, so this is something that we're going to talk soon. Okay, so that was the first one, mean. And that mean is ensembled mean. Okay, the other one is autocorrelation. So what is autocorrelation means? Autocorrelation means this. Relationship between two actually different time of that random process. So it measures similarity between the process at two separate time. But that separating time is by a lag, tau. We put a lag tau because most of, like for example here, this is T1 and this is T2, and this time is lag. Especially in actually stationary random processes, T1 and T2 not important, just this lag is important. So how much this lag is close, if the lag is close to 0, means those 2 points are so correlated because they are so close to each other. Correlated, I mean, in so many applications. Like for example, the diagram is like that, as you can see, and it's symmetric. Look at how beautiful is this. I don't know. I'm not sure if this is for that example, but as you can see here, is almost symmetric. So it means when you get close to 0, correlation or this testing similarity getting higher. Obviously, when two points are close, they are more similar, of course. So that's why it's going higher. In Gaussian process, this is a smoother. This is like a bell shape. Okay, so that's the definition of autocorrelation. Why auto? Why auto? I didn't explain that. We talk about cross correlation. We talked about correlation, but we didn't talk about autocorrelation. Did we? I don't know. Autocorrelation means by itself. Autocorrelation, it means X with a little bit later of that. Because we want to talk about the changing time. How they are varying in time. That's why it's called auto. Auto means itself. Okay, so the autocorrelation means a random process like xt, how much is different by itself in a little later. How this is changing. Okay, that's autocorrelation. We also have autocovariance. We also covariance and correlation are related, of course. In autocovariance, we always eliminate mean. We take mean out. Like we find deviation by mean. So if we make mean out, it's gonna be correlation minus mean square. Okay, so covariance, autocovariance is equal to autocorrelation minus mean square. We had that before too. Okay, so that's another thing. As you can see, this autocorrelation is related to tau or lag, not T1 and T2. That's interesting. And what else we have? We also have actually a stationarity that we're going to talk about the stationarity next slide. So they are all characteristic of random processes. So the key message, these functions fully describe a random process. They explain random process statistics with this characteristic. If you say, okay, mean is this much, autocorrelation is this, and autocovariance is this, and is a stationary. So those characteristics showing completely how this process statistically work. Good. Any questions? So this was characteristic of random process. So we talk about random process. We said random process is just adding time. And then we said, okay, random process has mean, has autocovariance, has autocorrelation, has some other characteristic that we're going to see later. And they are all fully describe the random process. When I'm saying something fully describe this, means you don't need anything else. You don't need the shape of them for all the infinite time. You just need to have autocorrelation. And as you can see, autocorrelation is a function. Function of what? Function of lag. Mu is a function. Function of what? Function of time. Sometimes it's constant. If it's constant, that's a stationary. And autocovariance is also function of lag. And function of mu2. So yeah. Time. Normally they are function of time. They are function. Sometimes this function is a stationary, just constant. Sometimes not. We can see examples. Okay, so that's random process. A stationary random process. Okay, so because random processes can be so complicated, sometimes it's good to start with something a little smoother, little simpler. We put some constraints at the beginning. One of the constraints that we put is this one. A stationary. A stationary means what? In general, anytime we say a stationary, if we say, oh, this system is stationary, it means this stationary characteristic is not changing by time. When the time change, characteristic of system in here is a statistical characteristic or a statistical properties, not changing with time. A statistical properties, what mean? Autocovariance, autocorrelation, they are not changing by time. So if the time changing, they are not changing, they stay stationary. That's why these systems called stationary. This kind of random processes are simpler to model and understand, of course. So we have different type of stationarity. The type that I'm talking is actually called weak stationary, or why is not going next page? Okay. Weak stationary or wide sense stationary, WSS process. So the weak stationary saying, so mean is constant, and autocorrelation depends only the time difference. Okay, and what is time difference? Is that lag or tau. So if you have these two characteristics, that system called stationary but weak stationary or wide sense stationary. Okay, so this is the type of stationary that the only type of stationary that we're going to talk in this class. Example, this is a stationary example. As you can see, if you get mean, you approximately get a constant value, and autocorrelation for two different times, it just depends on difference between these two times or lag. So this is one of the, what is called, let I zoom it up. It is white Gaussian noise. This is white noise. When I'm talking something white, means there is no correlation. There is no correlation in this, and but is Gaussian white. So is in top of Gaussian. So this is a stationary and also ergodic that we're going to talk about ergodic next slide. Okay, so that's definition of a stationary. Also, this is another example. This is a cosine, but random phase cosine. So we randomly change the phase. However, I just draw it for two realization. We just have two realization, but imagine there is 1,000 realization. Here is just going to be full of these cosine functions that they are differ in random phase. The phase is different. So one start here, and changing. And that's the amplitude. And this is time. This is time. So this is a stationary, but is not ergodic. You can't get enough information from one of them. You need to have all of them to can get all of characteristic of that random process. So we're going to see what is ergodic means. We're going to talk about that next slide. So that's what is the why is important? Why stationarity is important? Because of this characteristic. Because it makes life easier. Symmetry. Their autocorrelation is symmetric. We saw that it was like this or like this. It's symmetric. And what else? Autocovariance is exactly a function of tau or lag. We also know that. Oh, this is the main one. The power spectrum of a stationary process coming from Fourier transform of autocorrelation. So autocorrelation have enough information for us to get all characteristic of that signal, because the signal can be summarized with some frequencies. Those frequencies called power spectral densities. Power spectral densities is the basic of linear models. We're going to see that later. And for stationary random processes, we have this characteristic. The power spectral density coming from actually Fourier transform of autocorrelation. So if we have autocorrelation, we just need to get Fourier transform of that to get all the frequencies out. The frequencies that summarize all the random process. Instead of having lots of stuff here, We're just going to have some numbers. That's going to be power spectral density. When we have numbers, you can work with that. You can, so much stuff coming up. So that's amazing part that we're going to talk about that soon later, especially in linear systems. And this is a link between actually time domain and frequency domain. What is ergodicity? Ergodic system or ergodicity? Okay, ergodic is another constraint. We add another constraint in top of stationarity. We say, okay, in stationarity, we have so much good stuff, especially power spectral density, but what about we have a little problem because we need lots of outcomes, and these outcomes not nice, and it's not just not nice, we can't make them all. There are millions. What about if one outcome, one realization, one signal has enough information to summarize all the random process? If it's like that, that system called ergodic. And ergodicity coming from that. So adding some more constraints. So ergodicity is a property of a stationary random process. It needs to be a stationary first, and then ergodic. Okay, you can have ergodic but not a stationary. So it's a characteristic of one stationary random process that allows us to replace all actually ensembled means all outcomes with just one outcome. So here I also mentioned about average. So ensemble average and time average are equal. So time average means average of just one realization. In simple term, a random process is ergodic if one long enough sample is enough for all of its statistical information about that random process. That's amazing definition. Any question about that? But let me tell you the truth. I haven't seen ergodicity in my life. No application. I haven't seen that. I'm working in robotics for more than 10 years, or computer science. I haven't seen that. I don't know. Maybe it's too much. Too much constraints. But stationarity, yes, we have a lot. Okay, so that's something to know. Why it matter? Okay, because makes life easy, but it's too easy. It's not. Okay, in theory, random processes are defined over ensembled, but it's too much. Let's make it easier. That's why they created ergodic. Okay, I think it's enough to explain. So that's example. This is one random phase cosine example. The cosine example is one of the good non-actually ergodic process. So as you can see here, we made average of that, and this average, ensembled average, is approximately constant. Approximately, accept that. It's approximately. Look at that, it's so little. It's approximately constant. But if you bring, how many I have here? Why is approximately? Because I just considered limited. How many? 1, 2, 3, 5. 5 realization. This is just 5 realization. If you make it million realization, it's going to be line. You make it infinite, it's going to be line, of course. It's going to be line in 0. So that's why this is actually stationary. This function is stationary. But is it ergodic? It's not. Why? Because for this 5, for each one, as you can see, if you add for first realization, you get -1. For second one is almost minus, I don't know, 0.3. This is 0.4. This is 1/2. They are not even close to mean. They are not even close to mean. So it means it's not erodic. So this is a stationary because mean and variance don't change with time if the number of realization become infinity, of course. And not erodic because time and average is not equal to ensembled average. So that ensembled average is almost 0, but time average is not 0. If you add and average them together, it's going to be different. Okay, that's the mathematical things behind that. So mathematical form of ergodicity is like that. So if mean ensembled mean, so mean all of a realization together, like here, for example, this is, let me change that to darker. So this is like mean, 0. This is mean. And we just take one realization, and for that realization, this is just one realization, and for a long period of time, we add them together at the time, just for one. As you can see, this is average is gonna converge to 1. 0, sorry. They are equal. This is for how many? 10 realization. Okay, so in math, this is ensembled mean, and this is time mean. Time mean, it has a line in top. The time mean is just for one realization. For one realization, we add that up, but we limit that to infinity. T goes to infinity. This is approximately become equal. They are equal. So if they are equal, so the that stationary system is not just a stationary, is ergodic as well. Okay? Okay, but White process, this is something that we're going to use it a lot and a lot. White process is another characteristic of stochastic processes when samples are not correlated. They are uncorrelated. Samples are not correlated. Why is called white? Any guess? Why is not black? Why is not red? It's white. Why they call it white? Somebody answering me. because of white light. Like white light has all frequencies equally. It has all frequencies equally. So if you get a power spectral density, they are all equal. So that's why it's white. The white coming from white light. Yeah. So let's clean this up. So that's a meaning of white process. The white process, in white process, autocorrelation is constant in this form. This is in a continuous, is this familiar? Do you remember this one? Do you know the name? Is that delta function? Yes, that's a delta function that if you remember, if T1 and T2 are equal, that's infinity. But the infinity, that integral of that is 1. And if D1 and D2 not equal is 0. So, generally speaking, this R of T is diagonal. Because when it's equal, 0, 0, for example, is 1, 1, 1, 1, 2, or maybe a square of that. And here 0, here 0, 2. That was the definition of uncorrelated covariance. So, and autocorrelation becomes equal to covariance because there is no correlation. Okay, that's called white process. So every instant is independent. On every other instant, there is no memory. The power is uniformly distributed across all frequencies, as I explained. Hence the name white coming from that, and that's the sample of that. In discrete form, this Dirac delta function changed to a Kronecker delta function. Same. What else? That's it. Oh, example. Example, you saw white noise or white process in Kalman filter. Remember, in Kalman filter, we said the process noise is a Gaussian, white Gaussian. We saw that before in that example as well. Okay, any questions? Yes.
I have a question about the homework. So,
Homework?
in the homework, it says we're supposed to plot the covariance ellipses.
Yes.
Is that for every single point, or is that like the overall the overall covariance of like the entire?
I don't remember which the last one. That is still.
The last, just the last point.
Yes, last point.
Okay.
Last point of homework 3. Am I right?
Yeah. Like
homework 3. Yes. So and that was about Kalman filter.
yeah, it was the Kalman filter one that was
okay,
talking,
okay.
and it asked for the error ellipses, and I was just confused if you wanted like the ellipsis on each point or just the.
No, it was about. I think it was about Manhal distance. Am I right? I don't remember exactly, but if I mention something about that, you just need to show in 1 or 2. Doesn't need to go for that.
Okay.
Yes. So like yes, for demonstration part, I don't remember. I need to check it out.
Okay.
But I will check it out, and if something is not clear, I will notice that. I will mention that.
So
this
just to
one?
complete, it says overlay covariant to show uncertainty.
Yes.
But in the expected output, it's not mentioned.
Yes, as not mentioned. But if I didn't mention, you don't need. But if you have, just show it in a picture to see how that uncertainty, just for that point, doesn't need to be on all of the trajectory. No. Yes.
Thank you.
Yes. But I'm gonna check it and just see some clear.